Okay, hi everyone. So today we will present to you two different guided projects for this semester. It will be about the project I am going to present to you about exploring EEG classification and EEG based caption retrieval. So you will go through very interesting exercises. We will see that while I'm presenting. So the main problem definition here, when you look at images or when you see images, your brain generates some patterns of electrical activity that can be measured through EEG, electroencephalography. Can we decode what someone is seeing from their brain activity alone? This is a question that we are going to address here. So I will start with an overview about what is EEG and the data set that you will be using. And the first task you will be doing is to implement EEG encoder for classification of the images. And the second task will be caption retrieval. You will start with image caption retrieval, which is like very straightforward. You will get results without any training. And you will see the feasibility of applying that on EEG. So can EEG retrieve captions corresponding to the same visual stimulus that the person was looking at or not? So EEG, as you can see here, or electroencephalogram, it records brain activity through electrodes on the scalp, and basically it measures the voltage fluctuations, reflecting the firing of neurons in the head. The data that you will be working on, or any EEG data, there are some pre-processing steps, including band pass filtering. Like you remove some low frequency and high frequency from the data to be able to remove the slow drifts like sweating, or remove very fast fluctuation in activities like muscle activity or so. So the data is already pre-processed. We will be processing the data as is. We will not do any pre-processing step and see how it will go with us. So the data, they have recordings of EEG trials when people are looking at different images. And there are two different paradigm in this paper. Low speed, so each subject, this is the exact experiment they did. Like each image was like, each subject can see the image for 1 second, followed by a question. What is this image? And the second paradigm in this paper, it was very high speed, little bit. It's 0.1 second per image, but all from the same category. We will not be analyzing this one. We will be working on the low speed experiments. So for each run, continuous images the person was looking at, it includes 100 different images from 20 different classes. And the data is balanced, so each class has 5 images for each run. So this is one run, continuous, okay? And basically, each subject, if you look here at the right side, each subject has 5 sessions, meaning 5 different days. And each day of them, or each session, has 4 different runs for slow or low speed, and 4 runs for rapid images, rapid paradigm. The one we will be using is the slow one, okay? So each subject has 5 days, and each day has 4 different runs, and each run has 100 images. So the total number of images, as you can see here, for each session is 400 multiplied by 1, 2, 3, 4 session. Okay, so the total number of images in this data is 26,000 images that you will be using. And let's start with the first task you will do, the EEG-based image classification. Firstly, I will tell you about the original paper that published the data, how much accuracy they got from that. So they tested 3 different things. So within session, within subject, same subject, like the same subject within the same day, they have like 4 runs for this subject, 3 runs to be training, and the last run to be testing. So in this one, or they called it within session accuracy, they can get average of 10% accuracy, just 10%. But there is variability, like few subjects are close to the random chance, and others, random chance here is 5%. You have 20 classes, okay? And some individuals, like number 13, for example, it can get up to 14%. When they did the experiments across different sessions or cross subjects, they get little bit performance, like in the low speed. Let's look at the low speed. The high speed is very lower, much lower. But the low speed, they get average of 10%, 11%, okay, within subject and cross subject. So you will use the baseline model they implemented in the paper. I will show it to you right now. And you will implement new models, and hopefully you will have better performance than this one. This one is 10%. If you get 25, 30, I'm not sure, but that will be much improvement in this kind of classifications. There are 20 different classes. So here are the 5 models they implemented and they provided in the GitHub link here, as you see. And they use this one, fully connected network, in the tests they provided in the paper. So you will implement it as you will use that as a baseline. You can use EEG-net model. There are some baseline models. You can choose any of them and use. But the model that like we are interested in testing in this project, you will be working on, uh, it will be like it will handle different like multi-subject, multi-session. It should be robust enough to handle this variability between the EEG data from different session and different subjects. As you can see here, the data you have 122 different electrodes, and each one has 500 time points, which are 0.5 second, like half second, okay? And this data, you will extract feature from it. Instead of 500, you will reduce this number of dimensions through convolutional block. And then you will implement 2 different things: shared backbone across all the subjects, okay, and specific head for each subject. And the details, she will go through the details on the write-up when she will be presenting that. The second task after the classification, it will be caption retrieval. And in this task, you, instead of starting with EEG for caption retrieval, because we are still not sure if it will be possible or not, it is just feasibility study. So you will start with image retrieval. So the main model that you will be using for this task, image text retrieval, it is called CLIP, Contrastive Language Image Pre-training. And this model is very interesting. Like it has been cited like 44,000 times, I believe, and it's a recent one. It's not that much old. It can do zero-shot classification. It's a CLIP model. So it is basically can calculate the similarity between embeddings of images and text, okay? And this is very straightforward. It has 2 encoders, text encoder and vision encoder for images. So either of those text or image, it will be encoded in a vector, and this vector will be normalized to a unit length so that you can calculate the similarity by just multiplying them together. So 2 vectors, one for text, one for image, just multiply them together. That will give you the cosine similarity between them. So if they have similarity of 1, that means they are exact match or too much close to each other, in the embedding space. Negative 1, they are completely different from each other, okay? So in this case, it will, if you use this image to retrieve which caption will be closer or most similar to it, it will give the highest similarity to this one. So, okay, and there is similarity for the second one, third one, and so on. So it is basically you can use image to retrieve text, or the opposite. You can use text to retrieve image. So you can just calculate the similarity between them. And it is not restricted to image and text. So it has multiple different applications that are in the literature available, different variation, different improvements, refinement, like for different tasks, like zero-shot classification, image caption retrieval, as we discussed, or cross different domains. Some modifications can be applied on video text, like in robotics, or medical applications. If you fine-tune it a little bit, so it can you can provide some pathology or radiology images. So you can just query, I want to see images with whatever this pathology. It will retrieve those images. So you are searching, or this image, and you will retrieve similar description of them, and from those description you will retrieve similar image. So you can search for indirectly using an image to get similar image from it using CLIP. So it has a lot of different applications. Even some application went further than that for segmentation as well, not just description of the images. So it is very good model to learn about, actually. So you will be applying that as follow. Like, this is what you may need to do. You will start with downloading a pre-trained CLIP model. There are some variations of it, different capacities. You will choose a reasonable one. And then you will embed both image and text, the caption that you will be, we will provide you with the caption as well. And after that, you will calculate the similarity to be able, cosine similarity, or it's called the CLIP score here, to use the image embeddings to retrieve the caption with the highest similarity score. And the evaluation for that can be, there are different evaluation matrices you can use. BERT score, this score can calculate similarity between two different texts, okay? In this case, you search for what is the best, the high similar caption for this image. You retrieve some sort of captions, and you have the ground truth. Okay, so you can score that with BERT score. So this method of scoring, it is semantic scoring. It takes care of the semantic meaning behind the word. So it is not exact words, but if the meaning is similar, it will give you a higher score as well, unlike other lexical matrices before. And you will also need to calculate recall and precision. So recall is the retrieved caption is among the top 3, top 5, okay, or the top 1, and the average of that across all the sessions and subjects. And one more variance of it, which is class-aware recall. So the retrieved caption, the top one is not the same, but is it from the same class? It is a cat or train, like not the same caption, but it is from the same class. So we put this as well, so that because EEG data might be, it may not be the most discriminative, like in this level, like different images from the same category with different captions, okay? It may not be able to classify it pretty well. So you can also report with both, like recall level and class aware level, and the precision, the mean average precision. And the last thing, so when you calculate the similarity between cosine similarity using clip score between each image and the retrieved caption, after you train the model, not this one, in the EEG, you will train it, okay? So you will have to embed the EEG into clip dimensional space. After that, you will calculate the similarity between, in the image case, between each image and the ground truth caption, right? And you can also calculate the similarity between mismatched pairs of image text. And you can look at the distribution in the image case. So this is without any training. You can see clear separation between random mismatches and the ground truth. In the EEG, you will do something similar. So if they are like overlapping, that means the model is like it generates similarity similar to the random distribution, right? So there should be some separation, not that much. This is a model, the original model that we're trained like over how many million image, like 44 million or 400, like millions of images. This model is well trained. Um, so in the EEG case, you will not find that much clear separation, but let's see how it will go. So you see, this is exactly the summary of how clip work. You have image and caption, and using clip image encoder or clip text encoder, you will embed both of them and calculate the similarity. In the case of the EEG, you want to exchange the input data instead of image to be EEG, and the embedding will be EEG as well. The same vector with the same length to be matched with clip embedding space. So you will not use the image encoder, but you will still be using the text encoder of clip. So the EEG encoder that you trained already in the classification task previously, you can use it, okay? And you will project the output of it to be matched with the clip embedding space. So instead of in the classification task, you have softmax, right? Softmax layer. You remove this layer, and whatever the size of the layer before it, you have to match it with clip embedding space, which is 512 in this case. So whatever is output, 1256, whatever, you will just project it into this embedding space. And this projection layer can be just linear layer or non-linear, couple of layers with non-linear function. So you can test between like linear, non-linear, and see which one can work better. And you have also different options when you map the EEG data. You can, for the text encoder, clip text encoder, okay, it is well trained. Clip is well trained, and it knows pretty well how to map text into the clip embedding space. But this is with image. It was trained with images. But with the EEG, so you may try to keep it frozen as it is because it is already trained. But you may also experiment with some fine-tuning techniques. Full fine-tuning, you can try that, or you can try partial fine-tuning. Like it has multiple layers. You will go through that in the notebook after this. So you can, which layers you may think when you fine tune a model, if you have 12 layers, you will unfreeze first layers or last layer. What do you think? Anyone have an answer for this? When you fine-tune a model, you unfreeze some layers, right? You can keep the whole layers frozen, no updates for the weight, but you can unfreeze certain layers. If you have 12 layers, what do you think? Which layers, if you wanna unfreeze 2 layers, what do you think you can start with? First layer, 2 layers, or last 2 layers? First two. Do you have a reason? Anyone think otherwise? Okay. So we will start. Okay, you can test with first and see the results. I will be interested to see that, but I think it will be the last couple of layers because the first few layers, like in any model, they learn the like basic elements of the task under modeling. Like for example, convolution network with images, you start with some filters. Those filters will learn edges, like basic elements, right? And after that, while you are going deep in the network, you can get like with pooling and with much non-linearity going on, you can get more like objects wise, not just basic element. So you can test, but we included here, we suggest to fine tune last 2-3 layers, for example. Okay, and there is another option. Instead of doing partial fine tuning or unfreezing any layers, because the model is very large, like relatively, it's 150 million if you use the version called batch 32, for example. So instead of fine tuning the model or unfreezing it, keep it frozen, but still you can still update the weight while the model is frozen completely without any unfreezing of it. It is called using like one of the parameter efficient fine tuning techniques like adapters or LoRa. LoRa is called low rank adaptation. You will go through it. Look at this, for example. The original model is below here, okay? And the above one with moving arrows is with LoRa, injected LoRa inside. This is LoRa. So can you see, instead of full connections between 2 layers, there is like a bottleneck, right? So you saved yourself from a lot of computations when you are calculating gradients or for the training, right? The number of parameters you are training here is very lower, very low. So this is the point of LoRa. How it works, it is like that. The input X, for example, like originally it should go through the weight matrix, as you see here, the blue one. So when you inject LoRa in that, you inject low rank matrix, like this one. This one is composed of A and B. So it is the same dimension. B, for example, the number of rows is the same as W. And A has a number of columns the same as W as well. So can you tell me, for example, if you multiply those two matrices together, A and B, it will give you which dimension? If you multiply 8 by 1 multiplied by 1 by 8, for example, you will get the same dimensions of the original matrix here. Okay? So it is like, but with lower precision. Like if you train only A and B, so you are training, instead of training 8 by 8, 64 different weights, you are only training 8 by 2, 16 weights, okay? So you are training less number of parameters. And at the same time, when you train the parameters in A and B, you multiply them together, you will still get the same size of the weight matrix, okay? And after that, you will add them. So the original weight matrix will stay the same, but the adjusted weight matrix will be just the original matrix plus the multiplication of A and B after you train them. Of course, multiplied by scaling factor alpha over or R is the rank, the number of columns. So you can use, this is the bottleneck that you can see here. It can be 2, 4, 8, 16, any number. The original paper is very interesting. I advise to go through it, actually. And because they figured out that the original matrix is not, usually it is not a 4-rank matrix. It has a lot of like nothing to do there in some of the columns. And when they train LoRa here, okay, they found that the first few columns can catch most of the variability or variation present in the weight matrix. So they have a very nice experiment. They tested how to choose the best number of R parameter and alpha. So most of that is in the original paper, actually. Okay, so is this fine? LoRa adaptation? Okay. So the last thing is the loss function you will be using. In this model, you can, in the caption retrieval, when you use the EEG encoder and the text encoder from clip, you want to maximize the similarity between the embeddings, right? EEG and text, the two vectors. You have the cosine similarity between them, and you want to maximize that. So the loss function can be 1 minus this similarity. If they are the exact opposite, like -1, the loss will be huge, like it will be 2 here in this case. And if they are similar, if they are exact, like 1, which is not there in real world actually, but if they are 1 here, the maximum they can get, so it will be 0, right? So you want to maximize the similarity by using this loss function. And this is one kind of loss functions called knowledge distillation. You may experiment with another one, which is very, very interesting, actually. So it is like softmax. You have the original model, which is the teacher model, okay, which already the clip model, which is already pre-trained, and it you can use the information from it, how it maps the images with text, like what is the distribution between each image with each pair image text over all the distribution, okay. And that will be scaled by temperature parameter. Did you hear about this parameter before? So it is just softmax, but it is scaled. So this scaling parameter, I will show you the effect of that. So this is just softmax probabilities, for example, when the temperature parameter is equal to 1, like it is not there, it is nothing. So you can see here, class 1, for example, has 0.55 probabilities, okay? If you choose less temperature, so you are dividing the number here in the numerator with a low number, so it will be huge, right? So you are maximizing this. You will get a sharper distribution. Unlike if you get if you use a larger number, you will get like gradual decline in the distribution this way. Like that, like if this is the original, if you use low temperature, and this is the case when you will be, if you will experiment this this way of loss function, you will use a low temperature parameter. So the winner in all of those actually is the same. If you see number 1, for example, here is 1, 0.8, it is the same. It doesn't matter, right? But in the training process, it matters. So it means pushing positive and negative more or not much. Like it will matter during the training if you wanna extract the generic feature or you wanna exact. Even in text generation in GPT model, for example, GPT, if you during the generation, during GPT responses to you when you ask it a question, for example, if you use GPT API, for example, you can experiment with different. I believe that, or the pre-trained model, if you download GPT-2 or 3 or whatever, can be downloadable. You can experiment getting responses with different parameters, different temperature values. And for example, low value, which has the sharpest distribution here, it will give you like, if it is like confident of this, exactly this one. But if you make it like gradual distribution or a higher temperature, it will get like higher imagination in the response. It will get more, it will be more imaginary actually. Okay, so this is basically the temperature that you may use if you choose to use this one, or you can choose this one. So this one is the teacher model. And your model is actually the EEG to caption, right? So you will be using the distribution of those, and you wanna make your distribution of EEG and caption similar to it. So you will be using KL divergence as loss function to allow the distributions to be similar to each other a little bit. So this is called knowledge distillation. And the second component of the loss function you will be using in CLIP is contrastive alignment. And contrastive alignment, you will find all the details in the write-up about that. It's very straightforward. This is contrastive learning, okay? So I think you experiment that with before, like in some of the exercises you did. But in this case, because EEG data, like here, for example, if you say, okay, this caption is positive and everything else is negative, do you expect the EEG can really discriminate between this caption of a cat and consider that all other cats among the negative ones? Maybe yes, maybe no, right? So there is another variation we can use to insert a weight in the denominator here. And this weight, you can say, for example, if the image between is from the same class, I will put this weight as 0, for example. So that means you are excluding all the images from the same class of this caption from the denominator. So they are not no longer contributing negatively to your model, right? And if you can choose it differently. For example, you can see, like, you can find a way to make it not like 0 and 1. You can make it gradual. Like, you can use, for example, clip score between the original image and caption and see the other images, how similar they are to this caption, for example. And you can flip that, like 1 minus the similarity. But much straightforward, which we advise. We did some application and studies in that before we are presenting today. You try to be like class aware, just 0 or 1. That was working fine with us a little bit. This is clear, right? Is this fine? Okay. Finally, some of the preliminary results using the baseline model, which was implemented in the paper, the fully connected one. So what is this? This is caption retrieval, but class aware. This is the recall, class aware recall, which means that the caption, what is the score of being the first caption? Okay, not necessarily to be the exact caption, but at least from the same class. Okay, among the 20 classes. So you can see here up to 12%. So random chance 20 classes is 5% in this case, exactly as the original paper. Okay, so we got 12%, which is consistent with the finding of the original paper. They again got, for this subject that we tested, they got 12% as well, or 11. So this is just when we tested the baseline model, but instead of classification like the original paper, we tested it for caption retrieval. But the interesting thing is, when we checked the precision at class level, okay, can you see here that some classes have a high value close to 1. Basically, 0.5 here means, for example, in this precision, average precision, it means that the caption retrieved is among the top 2, if it is 0.5. If it is zero point 0.1, is meaning among the top 10. And the test sample here was 100 samples, okay? So that means that certain classes, 1, 2, 3, or even 4, 0.3 and above, so that means they were pretty well, but they did well. But the rest were close to random chance. So that was the baseline model that was implemented in the original paper. So the model you will be implementing, I expect it will be much better than that. So this is one of the matrices you will also report in this project. So to summarize the tasks here, you will start with classification. In this classification, you will use the original model from the paper. They have 5 models. You can choose any of them. They originally tested the fully convolution in the paper, fully connected network, so you can use that. You can experiment with EGNet or any other model of your choice as baseline, just to justify that. And the model you will be implementing, including backbone, generic across all the subjects, and heads, which will be subject specific. And you will be training on 3 sessions. Each subject has 5 sessions. We give you subset of the data of the subject that only has complete sessions, 5 sessions. So you will use session 1, 2, 3 for training, validation on session 4, testing on session 5, and then you will evaluate the classification accuracy and use the confusion matrix to see if certain classes perform better or not. For the second task, caption retrieval, you will start with get hands-on with clip for image caption retrieval, not for the EEG, using frozen encoders, either text or image, and you will evaluate the image retrieved captions using semantic matrices metrics that we described, clip score or BERT score, recall at class level, and precision. And as you saw, the 2 distributions were separate from each other. So clip score similarities between paired matches and mismatches. And after you experiment that with EEG, and I believe this is very, very straightforward, no training, no anything. You will just download the model and figure out how to make it work. And it will give you all of those scores. So this is very straightforward task. And everything you will implement here, you will just be using there in the evaluation, right? You will have the functions. You can apply it on the EEG caption retrieval, but in the EEG, because EEG is not trained in the text embedding space of CLIP, so you will experiment some fine-tuning, partial unfreezing, LoRa adapters. You are expected to choose one of the parameter efficient techniques like LoRa or adapter. So any of those you should try. And finally, you will evaluate the EEG retrieved captions with the same metrics you will be using in the images. Thank you. Questions? Any question? No questions, right? Okay. You want to start with the write-up? Going briefly through the write-up, right?
Can I ask, like, can you explain again the debias term for that loss function?
The loss function. It will be a combination between different loss functions. You can experiment.
Is there one that you have a weight for the denominator? I'm not too sure what that is. Can you explain again?
Okay, which one? You mean knowledge
The
distillation?
next one. The next page.
Which one you mean?
Oh yeah, this
this
W
one.
term. Yes.
Okay, so what this W term will do, right? So here in contrastive alignment, you are treating your samples relatively. You are not dealing with each instance individually, right? You are making this one to be separated from the rest, correct? So that means
I'm confused. Can you say, I'm still not too sure, like, what do you mean they are separate?
Okay, in contrastive alignment, you are dealing with each sample in your data as positive and trying to separate it from all other samples. And in this case, you can work with one caption, for example, for a train. And other captions, you are dealing with them as negatives and trying to separate them together in the embedding state. Okay. And those other captions can include also trains. And EEG data, we didn't test yet, but it might not be able to separate between them. So this is why we are saying you can consider that all the instances from the same class as positive and treat the other as negatives. So basically, if you assign weight to be 0 for all the captions from the same class as ZII here, as that means you are so similar captions or captions from the same class are not contributing negatively to your loss function. Is that clear?
Yes, thank you.
Welcome. Okay, so we will start with the write-up right now. So thank you so much. You want to present it from here, right?
Okay. I actually made some changes, so I'm going to download the latest version.
Can you pause sharing first?
Yeah,
I'll do that. Okay.
Thank you so much.
It's okay.
Oh, maybe we could have just used this.
There's no like keyboard right peripherals.
Oh yeah, that's true.
Cool. All right, I'm going to present my entire screen. You can.
Yeah, thank you.
No problem. Just check that everything's in order.
Okay. Hello, everyone. Let's do a quick walkthrough through the write-up, just so that you guys know what every section means. So Safwat gave a great explanation for what the task is and what you're expected to do throughout this project. In the write-up, we've arranged it in a way that's hopefully very clear for you guys to see, and it's divided based on, oh, sorry. Yeah, and it's divided based on what the different tasks are. So you can see that you have task 1, which is classification, and then task 2, which is caption retrieval, and all the specific subtasks that you have to do for each task are within those sections. Personally, like what I found really helpful about the write-up was the introduction and the project overflow section. In the project overflow section, the relevant sections are linked. So when we say, for example, create a data structure for training, you can just go to section 2, which is data set description, read through the entire thing, and then at the very end of the section, the exact task that you have to do is mentioned right here, how you have to do it, and then we have figures that hopefully explain everything. Is there a specific subsection that you guys want clarification on from the presentation that I can spend some extra time on? Okay, if mostly everything was clear, then I'm just gonna go through a brief overview of the project workflow, and then I'll talk in a little bit more detail about the model architecture that we'll be working with. And then I will walk through some of the code that we've provided you guys as a starter. So again, as a recap, the project workflow, we have 2 major tasks here. One of them is that given EEG signals from someone's brain, we want to figure out what category the image that they were viewing was based off of. And so for that, this is essentially going to be accessing the data, implementing the main architecture that we're talking about, implementing a baseline, and then running some evaluation metrics like accuracy to see how good the model is at predicting the category of the image. And then task 2, which is the really interesting task, is can we retrieve a caption that is most similar to the image that was being viewed? And that's where you really get to work with clip, as Safwat mentioned, and explore different losses as well as training strategies for clip, and then also different scores that you can use to do text-to-text comparison and see how good your retrieved caption is. A very brief overview of the main architecture that you'll be working with. So for both of these tasks, you will be implementing the same architecture. And by the way, like all of these are just suggestions. The flexibility of the guided project is that if you believe that there's any component that can be better or that you would like to try a different idea, as long as you can provide justification for it, you are more than welcome to try something different. But as a starter, this is the architecture that we've provided to you. The basic idea is that your EEG data is going to be over different times, different channels, and different sessions. So there's a lot of variability here because between one session and the other session, your electrodes can move. Between one subject and the other subject, the brains are different. So of course, that's a different source of variability. And so in the beginning, you will first process the data with a convolutional block, which will essentially help you downsample your original data and extract the features that we believe that the model believes will be most important and impactful in terms of predicting the class or the caption. All the subjects share a shared backbone, which is going to be of a transformer type. And homework 4 is going to deal with transformers. So you guys will get some introduction on what transformers are, how to implement them, and you can go based off of that for the shared project as well. For the project as well. And then because there is so much variability between subjects, the really cool thing about this architecture is that you can essentially create subject-specific heads, which are only trained on the data for that subject. So with a shared backbone, you're gathering information on, in general, what does the EEG to image mapping look like, or EEG to classification mapping look like. And then with the subject-specific heads, you are specifically trying to train on the idiosyncrasies of like one person's brain, which is super cool. And the added cool thing about this is that if you want to add a subject, so let's say that I train on 12 subjects and then I get data for a 13th subject and I want to add that to my model. Instead of modifying the entire model, I can just add another head and fine tune the head based on what I already have in the rest of my model. So this kind of modular structure is really cool for the kind of data that we have. And then finally, so this entire model will be shared across both the tasks, and you will begin training it in the classification task and then fine tune it in the retrieval task. The only thing that's going to change is the absolute last layer, which is the projection heads. So for classification, as you can imagine, we want softmax or some sort of probability over the 20 classes. But for the caption retrieval task, we want like a score or some sort of similarity metric with the caption. Or sorry, in this case, we want a similarity metric with the text embedding. So we want the EEG distribution to match the text distribution from clip. And so the projection head is something that you guys will have to experiment with to see what works best. And this is going to feed into your evaluation metrics as well. Other than that, the write-up itself is quite clear. Again, I know that it's a lot of text, it's like 30 pages, but try to refer to the project overflow section. That will very clearly denote like which section is relevant for which task. And yeah, hopefully that's clear. One thing that I will say is that the data set that we are using has some copyright laws. And so there is a Google form that everyone in the project has to fill out to get access to the data directory. The data set is all on PSC. So pretty much the only way to do this project would be to access it through PSC. It's a really heavy data set. It's like around 125 GBs. So it's pretty big. And we would recommend using PSC for something like this. The link to the Google form is right here. And you have this. And just fill it out. Everyone in the project group can fill it out. And once we have that from everyone in the project group, we will share the directory with you. Okay, any questions?
When will the project group be formed? Like,
sorry, repeat.
If I fill out the form that says I don't have a project group, when will a project group be formed?
Oh, I think we're working on forming project groups right now. Give us a couple of days. I think hopefully by Monday or Wednesday of next week, we should have them released.
Okay, thank you.
But the TAs are working on making project groups right now. Okay. And then the last component of the project packet that we're giving you is a notebook that talks about clip fine-tuning. So specifically, specifically in the caption retrieval for task 2A, which is image caption retrieval with clip, or actually not that one. When we're talking about the it's all the way down here. Yeah. When we are talking about training strategies for your EEG model and then your clip model, there are different strategies that you can use, as Safwat already mentioned in his presentation, to get you started on some of them. So specifically for frozen, partial unfreezing, and LoRa, we have a notebook that basically walks you through how do you load clip, how do I freeze my model parameters, how do I unfreeze some of them, how do I implement LoRa and stuff like that. I'm not going to run through this right now, but I would highly recommend checking it out as a starter code when you guys begin working on that section. The really cool thing about this notebook is that it has a lot of very helpful print statements that tell you exactly what are the trainable parameters, what is frozen, and you can very clearly see. So, this is essentially just loading clip. This is showing you what does clip look like. So you can see that there's a text embedding, there's a text transformer, and then there's an image transformer, which are the two main components of clip. You have a whole section on freezing and unfreezing clip. And you can see that if you freeze it, you have 0% of trainability ratio because all your parameters are frozen. And you can unfreeze like specific parts of it. So you can unfreeze just the text projection head, just the image projection head, or something like that. And then you have an entire section on parameter efficient fine tuning, which again is what you want to do. You don't want to train this really big 400 million parameter model all by yourself. You want to ideally select most of the high impact layers and only work on those. And so LoRa is one of the ways that helps you do that. And so this section walks you through different hyperparameters that you can use for LoRa based fine tuning. And then you can see again here, like with LoRa, the really cool thing is that the trainable ratio is only 2% or 0.02%, I guess. But despite that, like you can get really cool fine tuning metrics with something like this. Okay. And yeah, you're also encouraged to look into adapters. It's not included in this notebook, but hopefully this starter code is enough for you guys to get started into exploring something like adapters. Okay, any questions on the code so far? Cool, awesome. Thank you so much. We will hand it over to the diffusion team. All the best.
Is your computer or
We can use that, but we can use.
what about the walkthrough?
Yeah, also, guys, there's snacks on the table. If you guys just want to take them.
We can take a couple of minutes break and like have some.
Dude, what if I wanna walk through the code? Do you have local because it's like a zip or something?
Okay, I think we'll tell them to have it after. I think they're a little shy. I'm not going to do the other things. For the code, right? Yeah,
Do you think?
we'll have to do it with
So we just switch it now?
yeah, we can switch it. I mean, we'll have to join class.
This is the. Oh, the classroom. Okay.
Yeah, classroom.
What did you guys have for lunch? I had too much last night, so I didn't order. I had some fried rice. I was like,
Oh, nice. Yeah, it always happens at times. Cool. You want to plug in?
yeah. So, do I use my laptop's microphone or use that?
You should use this one. I think this will be plugged in. It's currently turned off.
Yeah. Yeah, close the dangerous.
Yeah.
Dangerous stuffs. Yeah, I guess I'll. Oh, so here. Hello, camera. Oh yes, sounds good. Cool. Guys, get started.
Yeah.
Okay. Hello, guys. We're gonna start the second version, like second choice for the guided project Diffusion, which was also the topic for a few previous semesters. And me and Sriharsha is gonna cover it. I'll cover the first half, and he'll cover the second. Then I'll do a walkthrough of the write-up and the code. And so let's get started. Currently, what you have learning in class is not about generation, right? You have a lot of classification stuff. You have some background knowledge on neural networks and how to do training, background propagation, convolutions, sort of stuff. But in practice, you only use them for classification, right? You have phases in the past homework, and you have like MCC in the first homework. You only figure out which class is it in. You don't really generate stuff that looks like what is given in the training set. But diffusion is helping you doing the generations task. It is the state of the art generation model in a lot of realms, of course. I think it came out to generate RGB images, then people use it to generate 3D scenes, videos, 4D scenes, robot controls. And they're now even using diffusion to do the sequence prediction stuff, actually. Dudes from our university. It's a preprint, but looks pretty cool. Yeah. So you're gonna implement a vanilla version of the diffusion model in this homework, and you're going to do the most simple, it's not most simple, relatively most simple task of generating images. So let's get started. Yeah, it's just like an example of the data you're gonna use. Where you have like a description of the class, and you have, okay, why is my and then you have a lot of samples for each class, and you're gonna make your diffusion model learn how to generate images from the classes. So mathematically, this process can be defined as trying to approximate this probability distribution here. You have a sample, and you assume that the samples are drawn from an IID distribution. And what you're gonna do is that you want to train a model to make sure that given an input of the image, well, okay, there's some discrepancy here, but you can just think of it as you're trying to use a model to approximate this probability. And to do this, there's a term called negative log likelihood. You might see this a lot. And the reason for doing this is because I think in these kind of scenarios, there's like you always involve some IID stuff, like independent identically distributed some sort of stuff. And when you just try to calculate the overall probability, you just get like the multiplication of a lot of densities. And if you take a log, you can break them up into additions, right? And expectation here is to approximate. Like in machine learning, you always do this. You have a mini batch of data, you approximate something by like you're supposed to calculate the expectation analytically, but you cannot do that because there's infinite many of samples. So you do this by assembling a mini batch. So this is the training objective. And the story starts from VAE. You see this in the lecture, but the professor might introduce it in a more detailed perspective. So we just do super quick walkthrough here. This is the overall architecture. You have an input, you have an encoder, you generate a latent variable, and you decode it back to the output. This is for training. Like for training, you need to go through every single part of the model. And during inference, you sample in the latent space and you decode it into the output. All right. So the idea is that you learn how to map. Like the latent variable is like you assume that there's a part of the input that is unseen, and then you train a model that first half it generates the unseen or latent variable corresponding to each input. That distribution is called the posterior, and the output is you generate the output given the latent. I think it's called the conditional distribution of the output condition on the latent variable. And if we write it out analytically, it's gonna look like this. And in probabilistic models, there's like an important tool or concept called variational lower bound. You basically lower bound the probability, the log likelihood, like which is the training objective without the expectation term, by the help of the latent variable. This is like how you derive this. I'm not gonna go through it step by step. You can try to look at it later. So it all boils down to these two terms, reconstruction term, which is the expectation under the prior distribution. Or is this the prior distribution? No, it's the posterior distribution of the log likelihood of the conditional distribution, and minus the KL divergence between the posterior and the prior of the latent variable. This is the result. And we assume that we're going to use Gaussian distributions for both of like the P and Q, the posterior and the conditional distribution. So we can use other distributions, of course, but it's just that Gaussian distributions are like first it is like considered to be the like if you sample a lot of IID samples, right, then you take the average, you just get an Gaussian. And so people use it a lot because it feels some kind of like it's like a natural distribution. And secondly, if you use Gaussian, you can get very good looking mathematical results. Yeah. So if we assume that we use Gaussian distributions for the prior likelihood, we're gonna have a problem because like this Q is Gaussian, P is Gaussian, and if you do backpropagation, the gradient won't go through, right? Because gradient is not defined for like it doesn't involve any like randomness. It should be deterministic. So the solution here is the so-called reparameterization trick, which means that if you have a Gaussian distribution, you can you have the mean and the variance, and you can do the sampling by first sampling a variable from the standard normal Gaussian distribution. Then you multiply it with the square root of the of your variance and plus the average or the mean. This is equivalent from sampling directly from the normal distribution, but it just allows you to go to make the gradients go through, right? Because of the law of the doing derivatives, yeah. And recall that we just actually covered this, and we want to minimize the negative log likelihood. So it is equivalent to maximizing the negative of the stuff of the part of like on the right of the inequality, and you can again do a lot of math derivations to figure out that this term can be worked out to be something like this. And the KL divergence can be solved, so you do not need to do any approximations. And so this is the final objective. Yeah. And keep that in mind. In DPM, it's like an extension of VAEs. You stack a lot of VAs together, so you have a lot of those posteriors, and you have a lot of conditional distributions. And in practice, the authors decided to make the forward process, what's it, backward? Yeah, forward process to, sorry, backward process to be, yeah, forward process to add noise, to add Gaussian noise, and a backward process to approximate the reverse process of adding noise. That's the intuition. And this is the design choice, like how you want to add noise. You have a lot of ways to add noise. It's just like they designed the way to add noise to be like this because it supports their derivations. So keep that in mind. And there's a property of this structure. It's called a Markov chain. And the property is that the distribution of one variable is only dependent on the variable that is one step later than it, because it's a Markov chain. And so this gives us a pretty good property here because according to the Bayesian rule, you're gonna have a lot of stuff multiplied together if it's not a Markov chain. But because it is a Markov chain, you can do this. And you apply the property of Gaussian distributions. You can replace this Gaussian here with variable from the standard normal Gaussian and do some derivations to arrive at this equation, where the alphas and alpha bars are defined on a noise schedule, like the noise schedule here, and you 1 minus noise schedule, and you like multiply them together to get the alpha bars to arrive at this, which means that every step in of the anti-noise, you can just actually calculate it one step using these equations. This is actually important. This makes training much easier, but just keep that in mind for now. Yeah, this is what we had. And the reverse process, we have to model the reverse of adding noise, which is analytically I think it's actually not solvable. So we're gonna model it. We're gonna assume that it's a it's like a Gaussian distribution. I think it's probably not, but we're just gonna assume it, and we're gonna again we call them reparameterization trick. We're just gonna model the variance and the mean of this distribution. And I think in practice the DDPM vanilla version doesn't really model the variance. It only models the mean, but the theoretical stuff is like the same for either you decide to do. So again, because of the Markov chain process, you can break the joint distribution to this Bayesian rule plus Markov chain. And recalling the VAE, this is the distribution of your data. And you want to make this as large as possible for the samples in your training set. And if you factorize them, you can get into something like this. And this is actually just Bayesian rule and the Markov chain and the stuff, the properties we just went through in the previous slides, and with a lot of Tauzic math. You can look into the paper, online blogs, or ChatGPT, Gemini if you don't fully understand this. That's what I did. So you arrive at something like this. The variational lower bound for the training object, the probability, the log likelihood of a sample in DDPM. And then it mainly breaks down into three parts. There's a reconstruction term, there's a prior matching term, and there's a denoising matching term. So it is pretty evident that the governing term is this denoising matching term, right? It is summed for t-1 times. It looks very complicated because like this is you can get this one step. These are all one step. There's no trainable parameters in this term, but this looks very, very bad. Like we have never seen anything like this. So we have to dive into this denoising matching term first. How do we do that? First, we need to figure out how to calculate this distribution of xt-1 given xt and x0. And like this is all in the paper. I'm not sure if it's not in the paper. Probably the paper is a bit succinct, but you can search for online blogs, ask chatbots, and I'm pretty sure that this is correct. And you will eventually arrive at these stuff. I actually borrowed this from someone else. I didn't make it myself. Yeah. This essentially tells us that although this looks very scary, it is just another Gaussian distribution with the parameters that we can calculate. Right? Because the alphas are deterministic, the xt can be calculated one step from x0. Yeah. And now recall this term. We have this q stuff. The p stuff is just one step. So we now calculate the KL divergence, and with Tauzic math you get this. And now if we collect our results, this is the q stuff, right? This is the definition of xt, and we just have the definition of the KL divergence. Now we plug it in, and you can calculate mu q. Mu q is just like this stuff here. You arrive at this stuff here, and xt and epsilon. Like epsilon is like the stuff you sample from the standard normal Gaussian to calculate xt, right? Because like you can calculate it one step, and which means that if you choose to model instead not the mean of the denoising process, like denoising step, but to model the noise term here, because the first term is not involving any trainable parameters. Well, there actually is. Well, is it? Well, no, sorry. Yeah, xt is the noised sample at step t. Epsilon is the random sample of standard normal Gaussian you use to get xt. So if you choose to let your model epsilon directly, you can simplify the training objective, at least for the denoised mean matching term, from this stuff to this stuff. I think there's no really good explanation for this. This is just math. You might want to look at it yourself, but that's what math tells us. Now the denoising matching term is basically solved. These everything here doesn't involve any parameters, doesn't involve any randomness. And if you define the sigmas, like in DDPM, they defined it to not contain any trainable parameters. So this is deterministic. The epsilon is what you sample, and if you no, as soon as you sample at epsilon, you can calculate xt from the one step like property, and then you take your as input that xt and the t to your model to predict the noise you sampled. Right, this is what we arrive at for the desample denoising matching term, and for the reconstruction term, because the model is taking RGB images, it is actually not continuous. So they designed it to be to look like something like this, and for the prior matching term, there's no parameters, so we're done. This is what elbow looks like, because for each T here, you get something like this. So when training, you can either go through the entire process for T equals 0 to T minus 1. You take a sum of all those stuffs here, you add them together and take a super huge background process on that. Or you can also make T being sampled from uniformly from all the time steps, which makes it even more simpler. And I think it is equivalent to doing the previous option where you just sum it and optimize. Right, so you arrive at this training and sampling algorithms. In the training step, you sample the initial input, the denoising time index, a random sample from the standard normal Gaussian, and you calculate xt, and you train your model to approximate whatever noise you sampled. And in the denoising, you have to go backward in time for every time step. You start from a pure noise. You calculate the noise that you think should be added at that time, and you approximate x0, and then you try to calculate the sample of the previous step. Yeah. You can look in the paper for details, I think. It's much more detailed. And now we come to DDIM. I think it's not going to be in the lectures, but yeah, whatever. And a problem, which is also a common mistake in BDPM when you implement it in your homework, is that the number of denoising steps must be exactly the same as the number of steps in training. You cannot skip any of them. You can try to skip it, but I assure you get random noise. So extension to that is that if we want to skip some steps in denoising, and if you look at the DDPM training objectives, okay, it might be clear here. Like this objective here, this is sampled. This is your model. This is just a scalar, and this is what you really have to calculate a lot. X0 is fixed, alpha is fixed, and so what you only really depend on is the marginal distribution here. If you want to, yeah, right. Like this, sorry. Wait, what? Oh yeah, this entire rule depends on the structure of the Markov chain. Like if you look in the slides, because we're adding noise in a Markov chain format, each step is a random noise, we arrive at this. So technically, if we can change the way we add noise while keeping the fact that the distribution of xt given x0 remains the same as the case in DDPM, the training objective is still the same, which means that you can train the model in your DDPM version, but just do the denoising in a different way. You should theoretically arrive at similar results. So that's what the authors try to do. They modify the way they add noise by conditioning it not only on the previous time steps input, but also on the initial input. And the math terms are like something like this. I don't know how they came up with this, probably in dream. but like they designed it to look like this, and it can be proved that that this conditional distribution still holds. And based on new definition, you calculate the elbow, you arrive at something like this. They prove that it is equivalent to the elbow of the DPMs up to a constant. The details are in their paper. I think it's too complicated to cover here, so yeah, maybe if you're interested, look into the paper. And with their new definition of the process finding noise, you're gonna do the sampling like this. Again, the details are in their paper, which means that if you look at this, the sigma t is the sigma t, like the entire reasoning process here doesn't really involve what's your choice for sigma t. And a trick here, or a feature here, is that you can set it to be 0, which will make the entire process deterministic. And if it's deterministic, which it means that you can skip some steps without harm. I think that's the main contributions of DDIM. And I think your homework, what you're gonna do for it is just that you're gonna implement the schedules that the DDPM guys have created. You don't have to worry too much about theoretical stuff. It's not like it is very helpful if you understand them, but if you still have some questions about it, it doesn't really affect implementing it. Just make sure that you typed in the Python equations correctly according to the papers and the write-up. Yes. Now I'll transfer it to Harsha to discuss LES and class-part guidance.
All right, cool. Thanks, Yuzu, for that. After a lot of inundating logs, I finally have a picture here. We'll now talk about what you're going to implement for the second half of the guided project homework. So this will be in the write-out from section 4 onwards. So we'll briefly cover latent diffusion models, classify free guidance, and metrics to evaluate your model's performance. And then we'll look through the code and see what exactly you have to change and where. So I'll keep it a little brief, but ultimately what we've discussed now, or if it's not clear, we're talking about diffusion in the pixel space. If you have to generate an image, that means you have to generate 256 times 256 different pixels. That's a lot of pixels, and naturally it exponentially scales the larger the image we generate is. So can we do better? So researchers then discovered that we can actually perform this diffusion operation in a latent space. That is an encoded representation of the final representation that we want to display or output. So instead of performing diffusion in the expensive pixel space, in an embedded space, say from a CNN or a VAE, we do diffusion there, and then finally unproject that into the final image resolution. This is ultimately what's known as stable diffusion, which is responsible for all of the amazing images that you saw come out through like bots like Midjourney or DALL-E 3 years ago. So it's quite relevant and it's still picking up pace even today. So again, briefly covering the role of the variation autoencoder. As I said, we have to generate this latent space somehow. We can't directly start off and like a 256 cross 256 small patch and then expect to generate something on a much larger scale. So to do this, we introduce a variational autoencoder to find our latent space. And without going into too much details, or rather summarizing what Yuzu told us, this is the objective function for the variational autoencoder. Breaking it down, there's two terms here. E is expectation of the encoder. Z is our latent variable. X is our input. And log p theta is just parameterization of the output from the latent variable. This is our reconstruction loss. And then this is our KL divergence loss, which essentially says we want our latent distribution to match our data distribution as close as possible. You guys might remember from maybe recitations or even class that the KL divergence essentially measures how similar two distributions are to each other. So broadly speaking, these are two very important terms that you will see in the code should you choose to take this assignment. Your task will be to implement the encoding part of the variational autoencoder that provides an input to the DDPM that we just studied, and then transform the denoised output of the DDPM back to your image space. on to the next topic. So this will be classifier free guidance. Uh, as you've seen so far in this on this noising or denoising process, we've not tried to condition our output. We've just said, hey, we want to model the data distribution of our input, but through a generative process, and get some output that belongs to this data distribution. But as you guys may have seen, if you prompt DALL-E or Midjourney, you input some text and you expect to get an output that broadly resembles that text. How do we do that? To study that, we have to study classifier-based guidance, which essentially what it did in the past was introduce a form of classifier and use the gradients from that classifier, say an image classifier, to denoise your output further in a more structured way. We won't be covering that too much because nowadays that's essentially obsolete because it involved training your own diffusion model and a classifier model, which is not really straightforward. It's very hard to train. So nowadays, what's performed is classifier free guidance, which essentially does produce some form of conditional generation, but most of the time we do not explicitly enforce any structure to our output. Sometimes we do, sometimes we don't, based on a certain schedule. So yeah, that's what I mean by the last point here, where we say that models are trained conditionally and unconditionally, which actually improves the quality and alignment of the generated sample. Quality can be in how well defined your edges of the images are, and alignment might be how likely is it that this generated image actually comes from the distribution that the model was trained on. Essentially, how much sense does this image make? Again, one equation here. Classify free guidance is implemented by interpolating between the conditional and unconditional score functions. I will not go into detail right now what exactly a score function is or where this log is coming from and how these equations interplay with each other. You will read about this more in the write-up. But again, this is the most important equation you have to deal with. This first term here essentially captures the realism of our image, and this is the conditional contribution, essentially the guidance that we get from the classifier. Now, your task in this assignment guided project would be to set up the code for classifier free guidance and write the necessary documentation. You'll also have to adjust the score functions for the reverse process. I know this equation does seem long, but most of it is given for you, and you'll be playing around a lot with just some parameters here to make sure or to evaluate the quality of your final output. So now we have our model, we're doing diffusion in the latent space, we're using a VA to come back to our image space, and we've also studied how exactly we can condition our image output. But now what? This is a generative task. How do we know if we've done a good job or a bad job? So now this is the problem of metrics. How do we evaluate the quality of a generated signal, or in our case, an image? Because in this class of generation, we don't really have a fixed label or a deterministic idea of what our image should look like. For example, a robot on Mars sipping matcha in a sunset caricature style. How would you evaluate which image is better or worse? Actually, I'd like to ask you guys, hands up if you think the first image here is a better representation of this prompt. All right, cool. What about the second image? All right, nice. As you can see, it's really tough to decide. And that's why nowadays not nowadays, since the start of image generation, we actually use a neural network to classify generated images or understand how relevant they are to each other. For what it's worth, this first image came from GPT-5, and this is Nano Banana. And I think the difference is stark. Like, this isn't even a robot. Anyways. So evaluating generation through images. So we use a popular metric known as the Freshet inception distance, which is abbreviated as the FID score. This calculates the distance between distributions of images with known labels and generated images in the feature space of InceptionNet. InceptionNet is a CNN network from Google that performed image classification. Now, when we find out the difference or the distance between the distribution of generated images and what InceptionNet has already seen, that gives us an idea of how close or realistic our images are compared to the data set it was trained on. Again, this is the equation. You will study exactly what these mean in further detail in your write-up, or obviously through classes or online resources. But ultimately, the takeaway is that a lower FID value indicates that the generated distribution is closer to that of real data, which is nice. Secondly, we also use just the inception score. This leverages the classification output of the inception network, unlike the latent distribution, which is what we saw earlier. And this score like this takes into account classification confidence as well as diversity. Again, these are important metrics to know how well we have generated an image or how diverse our images are. The takeaway here is that a higher inception score value indicates that the generated distribution is of high quality. This is the image. As you can see, our friend KL divergence pops up again. So it's really important when we're talking about machine learning and different distributions, say for image generation or language generation. So get used to seeing this a lot if you progress further in this field of deep learning. So that's broadly covering what you will be implementing throughout this homework. And those are all the necessary implementations. Afterwards, you can explore other techniques for generation. Yeah, so you'll be actively encouraged to explore different directions to build upon the quality of your diffusion model. You can say use a learned variance for your DDPM. I hope this term now sort of makes sense to you guys. You can explore different noise schedules and log their effects. As Yusuf said, it's very important to choose a good noise scheduler because that allows you to train your network more efficiently or improve the quality of generation. Lastly, and this is something I'm a big fan of, is maybe trying something else altogether, using a diffusion transformer as your backbone model. So diffusion transformers are very popular now. As Yuzu said, diffusion is almost ubiquitous right now. It's being used in every field. And over there, only diffusion transformers are able to provide the scaling that's needed to perform these high dimensional tasks. So yeah, while the so far we've covered what's necessary to be implemented, and yeah, you can obviously go beyond, and the TAs will be happy to discuss that with you. Now, Yuzu will talk us a little bit through the code and tell you guys what you need to change, what the different files mean. But before that, do we have any questions about the entire thing, or maybe from LDMs onward? What's up?
Will we be
A
posting the
subset of
slide?
ImageNet. A subset of ImageNet. Yeah.
Any other questions?
Will this slide be posted?
All right, cool. Also, I'd say don't leave yet. We do have fees on the way.
Are they in the main? Oh, never mind. We'll just go over the write-up first. This is like a shorter walkthrough of DDPM. You can see some math equations there. I don't think it contains the detailed math reasoning. You might want to look for it yourself. But what it includes is the mathematical equations you have to implement in the code. Something like this. And we just talked about the training objective is to model the noise. And given our specific task, you're going to take in an RGB image, and so the noise will also be some like some noise that has the same shape as your image. And so you're going to use a UNet, which is some form of convolution network that first downsamples it and then upsamples it, and you have some some concatenation between the denoising part, sorry, the downsampling part and the upsampling part. Yeah. So you downsample, upsampling, and you have some concatenation for the same resolution at the processes, and you predict the noise here. It's just a design choice. We will make you implement the unit, but you can try something yourself, like the diffusion transformer. And this is gonna walk you through what training and inference we'll be doing. And this is the part for IIDM. the equations. I think you should have seen in the slides, and how you do inference. And now is an introduction for LDM. You're gonna use the VQVAE for that, to generate the embeddings, and CFG. You get like, I think this equation is worked out from the score function. Right. So yeah, the write-up contains the math you have to implement, not the detailed reasonings. If you really want to know how you can arrive at the arguments here, you probably want to look at the papers. You probably will also want to look at some online blogs and ask chatbots for something. So this is basically the write-up. And for walkthrough of the code, if we will share this later, and if you download it and extract it, you're gonna see a structure like this. The main function, the main script you're gonna run is string. There's a lot of command line flags here. You can pass arguments inside. There's default values for that. Make sure you understand what they do. I think what you should at least do is you should download the data, set it up, download the VQVAE weights, and pass in as arguments the directory of them. And this is the main file, the training file, and the inference file here. You're gonna run inference and generate samples. But I think there's a few. You also generate a few samples on training as well. Will you do it? Yeah, you do it. But anyways, and the config file here defines it will override the command line arguments here if you provide meaningful numbers here. And the model folder contains the VQVAE and the unit. And the unit is for denoising, and the VQVAE is for putting your input image into some latent space first. You should not have to touch anything here, I suppose. You just run it. Wait, oh, you should have to do this. Okay, sorry. You have to do the class embedder. I think this is for passing in your input and generating the embeddings. But I think for the rest, you for sure should not have to touch it. You don't have to touch it. And VAE, you 100% don't have to touch it. So the only thing you have to implement for the unit is this. And the pipeline is what most of the forward backward stuff where it resides. You're gonna calculate class embeddings, time embeddings, calculate those like noise samples at each step, and you control how you call your how do you calculate the noise, how to call the models, how to calculate the loss, something. I think it's mainly here. Yeah, and you have two files in the schedulers for DDPM, DDIM because they apparently have different forward process to noise. You look looking at this yourself. But what you have to implement is mainly here the two scheduling, the DDPM, and a little bit in class embedder, and we will play around with arguments in your training. And I think the utils here, checkpoint, I think it will be pretty important if you use PSC. It allows you to save your checkpoint on some directory that you specify, and if your allocation stops, you can load it back. You don't have to train from scratch every time. Yeah. Well, I guess that's basically it. Any questions? Well, we'll be holding office hours for the guided projects, I think, right?
Yeah, they will be.
So if you have questions after you have looked into the details of the homework, you can ask questions in homework. Sorry, in office hours. But I think it'll be it for now. Yeah.
Yeah, cool. These are the two choices you have for the guided project. And obviously, if you have any questions, post on Piazza, or you can reach out to us individually. But I think that's it.
We'll post it later. Yeah. Yeah, maybe tomorrow. This week, about this week. Hopefully, yeah. So I'll just stop sharing and I'll just disconnect.
Thank you.
Hey, are there any questions on Zoom? All right, cool. Thank you.
Thanks, guys.